All right, so good morning, everyone. Welcome back to H21 Lab after 2 weeks without lab. I hope everyone enjoyed last weekend after the midterm, no projects and everything. So today's lab is going to be about unordered maps and sets and also enumerated classes. And all of this stuff is going to be really useful for project 3, so just keep that in mind as we go. So today's agenda, first we're going to go over unordered maps and sets. We're also going to go over Enum Classes, Emplacement, using declarations, and finally we will go over this week's handwritten problem. So some announcements before we begin. Lab 6 is due this Friday, October 30, and Project 3 will be released shortly, sometime this week. So for this week's lab assignment, the only graded component will be the feedback forms. If more than 75% of the class submits it, everyone will get credit for it. And we really appreciate this feedback, so please take the time to go ahead and submit the feedback. Also for the instructor feedback, especially this semester with everything being remote, we really want to keep improving and helping you guys learn better. Other than this, there are also optional ungraded questions. So these are every week's graded assignments, but they won't be graded. We still encourage you guys to go ahead and look at those because it's good practice and it'll help you learn the content better. And also remember to submit the handwritten problem by Friday on Gradescope. And the midterm grades will be released soon. We're working on that, so hang tight there. Okay, so now going into the lab. If you guys have any questions, go ahead and type them into the chat or unmute yourselves and ask them. Okay, so maps and sets. This is kind of a throwback to one of the earlier labs, I think lab 3, where we did is anagram. And basically we wanted to determine if two strings were anagrams, which means if each letter in the word had the same count in both words. And we required a constant lookup for how many times a character occurred, right? Last time we only had 26 possible characters, so we could only have alphabetical characters, right? So a vector of size 26 worked perfectly, and we told you not to worry about any other characters. But now we're trying to think, what happens if we have things like exclamation points or asterisks or emojis? Or if we didn't want to index with numbers, then having a vector wouldn't be as useful anymore, since we couldn't limit our values to only these 26 values. So instead, what could we do? And this is kind of what we're going to get at with the unordered maps and sets today. So just keep this in mind. Keep this in mind and think of how you would edit this to, instead of mapping from only the alphabetical characters to counts, how could you map from more things to the counts again? So some more motivation before we get started with maps. Let's say that we want to store the names of every student in H281. And every student has a unique ID. And this ID is only in the range of 0 to 750. And we want to query this ID in constant time. This is very similar to the previous problem, right? Because we have a limited number of IDs. So what we could do to solve this problem is hold all of the names of these students in a vector of strings and index by the student ID. So for example, we would have a vector with the names Bob, Anna, etc. And if Anna's ID is 1, we would go to the index 1 in the vector. And that would be great. Now what happens if instead of using an ID, we want to use a unique name? And this unique name is a string of ASCII characters. And we still want to query by in constant time. So we could still use a vector, right? But it's not as easy to know where to index into the vector because we don't really know where each unique name goes to. So now we need to find a way to kind of map from unique name to an index to know where to put each unique name. So instead of using a vector, now we can use an unordered map. and this one will index with unique name rather than with like just an integer. So instead of having something like before where we had like Anna and then Bob and so on in a vector, and we indexed with like an ID, we would actually have like unique name mapping to Anna and another unique name mapping to Bob. And this still gives us constant querying and access into the names of these students. Okay, so now say that we have a struct for each student that contains their unique name, their full name, and a vector with their grades. So this would be, we would want to use a map that goes from the string, so their unique name or their name or anything else, to a student object. And then we can write a function, so get full name, that takes in their unique name and goes into this map and search with their unique name. And this part will return a student object. So your key to this map is a string, and the value that it returns is a student object. And we can use this to get their full name like this. And in a similar way, we can also use our map to edit the values inside of the student struct. So if we have this function add grade, we can query by unique name again, and this will return the student object. And dot grades gives us access into the vector that keeps all of the students' grades, and we can push back one more grade into this vector. So what are some of the good things about using an unordered map? So imagine that a unique name is between 3 and 8 characters. So this gives us more than 200 billion combinations of possible unique names. And we don't always want to use all of those combinations, right? Like we most likely won't need to. So using an unordered map allows us to only consider the unique names that we have seen, so only the ones that exist. We don't need to keep space for all the other combinations. If we use the vector to keep all of our like student structs, we would need to, if this vector was sorted, like say by like alphabetical order or something, searching would still take log of n time if we use binary search. However, if we use the map, we can simply index into this map using the unique name, and this will return a student object in constant time. So this is like the main thing about unordered maps. They give you constant access into every object inside of your map. Okay, so now how do you use an unordered map? So an unordered map goes from key to a value. And these keys have to be unique, which means that you can't have, like, for example, like 2 of the same unique names mapping to 2 different things. They do need to be unique. And they are not sorted in any particular way. So that's just something to keep in mind. The complexities for finding a value with a key or for inserting a new key into the hash table or the unordered map would be an average of big O of 1 and the worst case of big O of n. But the important part is that we have an average constant time lookup and insertion. And your keys must be hashable. What this means is that for each key, you need to be able to compute an index for this key. And most of the primitive types or all the primitive types in string are hashable by default, so you don't need to worry about that. So anything like ints, characters, strings, all of those can be hashed. So you can create maps really easily with those. And the elements in this map can be retrieved as a pair. We're going to look at pairs more closely later in the lab. But basically, the first element in the pair will represent the key. And the second element will represent the value. So for example, if you're going from a string to an integer, and you have like Anna and a 3, this is a pair that would be kept in your map. And the first is the key and the second is the value. Okay, so a pair is a data type that wraps 2 values, and they can be of different types, just like they were in the previous example, and they get treated as a single unit. And they can be accessed, the key and the value, or the 2 elements in the pair can be accessed using first and second. You can imagine it as being implemented like this. Oops, sorry about that. Like this. So if you had a pair where like first is equal to Anna and second is equal to 3, doing pair dot first would return Anna, and pair dot second would return a 3. These are 3 ways of creating a pair. All of them are valid, so you can use whatever you like find more readable or more understandable, and just make sure to include utility in order to use pairs. This is what I was talking about before. If you want to access the elements inside of a pair, you just need to access the first and the second elements, and you can modify them, you can assign them, you can do anything you want with them, basically. So here initially, first used to be pilots and second was 221. So we just changed them to be math and 217. Now, pair comparisons. So 2 pairs will be equal if the first and the second values are both equal. So they both need to be equal in order for the pair to be equal. If you're using less than and greater than comparisons, you will first compare the first element, and if those are equal, then you would look at the second element. So for example, in this pair where you have the first as a string and the second as an integer, you would compare every character in the string, right? That's how string comparison works. So here, if you're asking if pair 1 is less than pair 2, from the first character, you can see that a P is more than C. So this would return false right away. But then if you look at these other 2 pairs, you would go through every character, basically, and determine that the first is equal. So now we need to go and look at the second. And 2 is less than 3. So if we are asking if pair 1 is less than pair 2, we would say that it is, because parrot and parrot are equal, but 2 is less than 3. So this returns a true. Okay, so going back to unordered maps, these are some of the things you can do with a map and their effect. So say that you have an unordered map from int to int, and let's say that it's called map. Okay, so going into your map with your bracket operators returns a reference to a value. So whatever 1 maps to, say that we have like a 1 mapping to a 3, this would return a 3. And you can also use it to change the value of 1. So you can assign it like this, and now 1 will map to a 2. One thing to keep in mind is that if 1 is not originally in your map, using the operator brackets, the bracket operators will actually create this entry. So for example, if you do like something like cout map at a 1, this will go into your map and create this pair. So it'll create a pair for you, which is not always what you want. So just keep that in mind as you go through the project and everything else. So something you can do to avoid this is use .find. So .find, it takes in a key. So for example, here we can do .find 1. And if this key is in the map, then it returns an iterator to the key value pair. And if it's not, then it returns an iterator to the end. So this way you can tell if this iterator exists, then you could cout it, for example, or do anything you want with it. And if it doesn't exist, then, well, you do something else, right? Okay, so then we also have .insert. This one takes in a key value pair. So for example, you can .insert 1 and 3. And it creates this entry in your unordered map from mapping from 1 to 3. The return type for this function is a pair. It returns an iterator to the pair in the table. So it would return an iterator to this. And it also returns a bool. So if it actually got inserted, it returns true. But for example, say that you have this 1 and 3 here already in your map, and then you try to insert 1 and 5. The key 1 already exists in your map, so you're not actually inserting anything into it. So in this case, insert would return an iterator to this pair and false because it didn't actually insert 1 and 5. Insert or assign is pretty similar to insert. It does the same thing, except that if something like this happens, it will actually go and change the value of 1 to be a 5. So if it inserts it, it returns true. So insert returns true, and then modifying or like assigning returns a false. So in this case, again, inserting 1, 5 would return a false because it's like modifying the entry in the map. .erase will remove a key value pair from a hash table. So if you wanted to like get rid of this one, you would do of this entry, you would just .erase and iterator to it. And then .begin and .end return forward iterators that you can use to traverse through the whole map in some order. So again, this is an unordered map, which means that you can't guarantee that they will be like traversed through in like a certain like specific order. So it just happens in some order. That's just something to keep in mind. Okay. So now these are some examples of adding and accessing elements inside of a map. Again, if you guys have any questions, like feel free to stop me or just send a question in the chat and I'll make sure to answer all of those. Okay, so here we're looking at a map that goes from name to favorite color. So we have key values of names and values of favorite color. And this is something that we're going to look at later in lab. But this just basically means that name is a string and fave color is a string. And every time you say name or fave color, you actually mean string. Okay, so we have this map, and using the bracket operators, we'll create an entry inside of this map. So when we execute this line, we will put in Kevin and orange. So this is the pairs. These are the pairs that are created. Kevin and orange, and then Violetti and gray. So this is what we currently have inside of our map. So now when we go and see out favorite colors at Violetti, we will go into our map and look for this key. And that would return gray, right? So using the bracket operators returns a reference to your value. So that's why this would print gray. Okay, so now we can also use the .size operator on our map that returns how many pairs you currently have in your map. Since we have 2 pairs, that'll print 2. Okay, and now this is an important part. So we can go into favorite colors, and if we use the brackets operator to look for nobody, currently we don't have a nobody name inside of our map. But because we use the brackets operator, that's going to create a new entry for us, even though it doesn't currently exist. So this will go into our map and say that nobody maps to an empty string. So when we see out favorite colors at nobody, it'll print an empty string, even though nobody was not in our map before. This will create a new pair that goes from nobody to an empty string. Right, so the empty string gets inserted into the table. Okay, so now if we print the size of favorite colors, I'm gonna go back to the previous slide just so you guys can see that. Now we have 3 entries, 3 pairs inside of our map. So when we print the size again, we're going to print 3. Okay, so again, this is something that you want to be careful with. You don't always want to create an entry if you didn't find one in the map, right? So just something to keep in mind. And a fix for this, say that if you wanted to access nobody, you didn't actually want to insert this into the map. You wanted to do something else, or like tell the user nobody is not in the map, or something similar to this. What could you do in this case instead of just accessing with the bracket operators? So this is where find comes in useful. So say that input name was nobody. If we go and try to find nobody in favorite colors, this is not currently in our map. Our map only has these 2 pairs right now, right? So the found IT would be an iterator to the end. So that would return favorite colors dot end, which means that this value is not in the map. So we would see out name not found, nobody. Which is great, right? Because now we're not accidentally adding in a new key value pair into our map, right? So that's cool. But instead, if we say that input name is or Kevin, this will return an iterator to this pair. So again, an iterator gets dereferenced kind of like a pointer does. So we use the arrow operator and we access the first, right? Because this is an iterator to a pair. So found IT will be an iterator to a pair with or Kevin and orange. So found IT first will see out or Kevin, then their favorite color is the found IT dot second, which is orange. So this is just like a different way to access the pairs inside of your map, and it's better because it makes sure that you are not accidentally inserting like values into or key value pairs into your map when they don't exist. Now just looking at some performance, and this is again something that will come in useful in the project. So you need to avoid multiple lookups inside of your map. So in this first example, we are going into our map and trying to find X. So we're looking for X1s. So if F exists, then we want to see out its value. So here we are going into the map and using the bracket operators to look for X again. So we're looking for X a second time. So we're looking for X once with find and once with the bracket operators, which is not great, right? We should try to only look for this value once. So the way to do this would be to actually save an iterator to the pair inside of the map. So you look for X1s and you save an iterator. And now if this iterator is not the end, so if this key exists inside of the map, you can see out its value by dereferencing the iterator and printing the second of the pair. So instead of having to look for this key twice, we only looked for it once. And this will make your performance better. And this can get even worse, right? So say that you know that X is inside of employees. So in this example, we would have like, say like a struct employee that has like a salary, this is an int, a string title, and an int years working. Okay, so we have a map with multiple of these like employees. So if we go in with the bracket operators, remember every time we use the bracket operators, we're looking for something in the map. So we have to like hash the key and go into the map and look for it. So if you do this 3 times, each time you will be computing the hash index and having to go into your unordered map and search for this, which is not great, right? We saw last time that we can do this in one lookup, which makes your performance a lot better. So instead, these 2 ways are both valid. So in this first way, you save an iterator to a pair. So again, the pair would be whatever the type of X is. Let's say that it's like a string and an employee struct, right? So now that you saved it, you can simply look at the employee struct, which is the value. So you go through second and you get whatever like number you want to look at. So you only have to do it, you only have to look for this value once. And this is really similar, the second one, it's just slightly better style. So you go into your hash table and you look for this employee, and then you save a reference to it. Remember to save a reference to it because our employee struct could potentially be really big and we want to avoid having like unnecessary copies of it. So if we save a reference, we don't create a new copy to it. Okay, so then we can access it same as before. This is the value, so you can simply like do .salary, .title, .years working, and you can do anything you want with that. But the important part of this slide is that in this example, we're looking up X 3 times, and that's not good. And in these 2 examples, we're only looking for X once. Okay, now we're going to go over a couple multiple choice questions so that you guys can get some practice. So the question is, for which of the following applications would a hash table not be appropriate? And select all that apply, right? So it can be any of these 5. So let's go through them in order. If you think that they are not appropriate, like thumbs up into, or like send it in the chat or anything you feel comfortable with. So printing out all of the elements in sorted order. Do you guys think an unordered map would be, or a hash table would be appropriate for this or not? And I'll give you guys a little time to think of it. All right, so I'm seeing a lot of no's in the chat. So 1, printing out all of the elements in sorted order, that's not an appropriate use of a hash table. As we discussed before, the unordered map doesn't keep a specific order in it. That's why it's like unordered. So if you wanted to print all of the items in like some sorted order, you could not really use a map for this application. Now, how about storing passwords that can be looked up by unique name? Would this be appropriate or not? All right, I'm seeing a lot of yes in the chat. So yeah, this would be perfectly fine. this would be really similar to some of the other examples we've looked at where we want to kind of map from a string, I guess from the password. Oh shoot, never mind. So you're looking, your key would be your unique name and the value would be the password. So a map would be perfectly fine for this. Okay, so now number 3, returning a person's name given their phone number. What do you guys think about this one? Yep, again, this is perfectly good application of a hash table. We would be going from a phone number to a name. So again, similar to what the other applications we've looked at. Number 4, finding the k's largest element in an array. Would an unordered map be useful here? Nope. Again, k's largest, there's no way for us to know how like the order of these elements in our map, so we wouldn't really want to use the hash table here. And finally, number 5, creating an index for an online book. Would this be useful? Yeah, so this one's a little trickier, but the answer again is yes. Because an index really, it just maps from like, say like a section to a chapter or something like this. But the main idea is that you can map from, say the name of a chapter, for example, to a page. Or whatever, however your book is divided, I guess, but main idea stands. You can map from one thing to another. Yep, that's correct. We got the right answers. Okay, now symmetric pairs. So 2 pairs are symmetric if we have our first pair A and B and our second pair C and D. So these pairs are symmetric if B is equal to C and A is equal to D. And suppose that we want to find all the symmetric pairs in an array. And we know that the first element of all pairs is distinct. So for example, we get these pairs, the symmetric ones would be 11, 2, 2 and 11, and 49, 38, 38, 49, right? Because 11 is equal to 11, 2 equals 2, and same with the other one. So what would be the average case time complexity of accomplishing this task if we use the most efficient algorithm? And then if hashing is involved, you can assume that search and insert works in constant time. I'll give you guys some time to think of this. When you think you have an answer, just type it in the chat. Yeah, so you can take a minute for this. So do you guys want some more time to think about this, or would you rather just go through it together? All right, so we can go through it together. Okay, so we are given pairs and we want to find the symmetric ones. So we want to think of how we can use a map to accomplish this task, right? So we definitely need to look through all of the pairs in order to determine if they are symmetric, right? So we can kind of like immediately discard constant time and log n time, since we do need to look at all the pairs to make sure that we're not like dismissing any possibilities, right? So, okay, so now what we can do is we can go through the list of pairs and save them in a map. So our map can go from from A to B, for example. So we would look at this first pair and we would save 14 goes to 23. And now when we look at the second pair, we save it in our maps, but we also want to see if there's a symmetric pair already existing in this map. So we would look for a key of 2. In this case, there is not a key of 2, so we know that there's not a symmetric pair for 11, 2. So then we look at the next pair and we save it, 52 and 83. And now we want to check if there's a symmetric pair for this one. So we go into the map and we look for 83. 83 does not exist as a key in our map, so we don't find a symmetric pair. Next, we save 49 and 38. We look for 38. It's not in the map, so we move on. Okay, so now we insert 38 and 49. And when we look for 49, we find that this exists in our map, right? It returns this pair. And so now we compare the value of this pair, which is a 38, with our key to our current pair, which is a 38. So these ones are equal, and these ones are equal. So we know that this is a symmetric pair. So we would save it, we would save these two pairs, like 49 and 38, and 38 and 49. Oops, sorry about that. Okay. So now we look at the final pair, which is a 2 and an 11. So we look for 11 in our map, and this already exists. And the value of this pair is 2, and our key is a 2. So this is another symmetric pair. 2, 11, 11, 2. And we did this in one pass of the whole array, which means that this is a big O of n, or biggest theta of n complexity, since we only had to go through the array one time and look at each like element once. Right, so that's kind of the explanation we had. Check if the current second element is in the hash table, and if it is, and the first element matches, then we have a symmetric pair, right? So kind of what we demonstrated in the previous slide. Okay, now for some interview problems. Maps come up a lot in interview questions, so always something good to practice. Say that you're given a vector of integers and you want to find the first non-repeated integer. So for example, if we have this vector of integers, we can see that negative 234 is repeated, 2 is repeated, 1 is repeated. So 10 would be the first one that is not repeated. So again, take a minute to think of how you could solve this using maps, and then we'll come back together and discuss a possible solution. Okay, so do you guys want another minute to think about it some more, or would you rather just go through it again together? All right, yeah, we can go over it together. Does anyone have any ideas that they would like to share before they go through it? Okay, that's fine. So something we could do is use a map that it goes from an integer, so the integers that we see inside of our vector, and goes to the count. So we save how many times we have seen each of these integers inside of the vector. So for example, the first time we see negative 234, we map it to a 1. The next we see a 2, and again we map it to 1, 1, 2, 1. Okay, and then now we're seeing negative 234 for the second time. So we increment its count from 1 to 2. Now we're seeing 10 for the first time, so we create a key 10 and the value 1. Same for 72. Now we're seeing 1 once more, so we change its count from 1 to 2, and the same for 2. Okay, so now we know how many times each element in this vector appears. And the question is asking for the first non-repeated integer. So we can see that 10 and 72 both aren't repeated, right? They only appear once. But we want the first one. So something we can do to find the very first one is to again go through each of the elements in the vector. And the first time we see a count of 1, we return that integer. So negative 234 would return a 2. So that's repeated. That's not the one we're looking for. 2 also returns a count of 2, which means that it's repeated. We don't want that. Same with 1. 234 again would return a 2. Finally, we look at 10, and this one has a count of 1, and it's the first one we see. So we can just return 10. Okay, so we are going through this vector twice, but each time we only do a constant amount of work for each of the elements, which means that our time complexity is big O of n, and our space complexity is also big O of n, because we're saving a map entry for each of the elements in our vector. Okay, so now what happens if each element can appear at a most twice? How could we improve the efficiency of the solution that we came up with before? There's a way to make this more space efficient. So if we know that each element appears at most twice, the second time we see it, we can just remove it from the hash table. So going back to where we drew the solution. So when we saw negative 234 for the second time, we can just get rid of this entry, since we know that we will never see it again because it appears at most twice. Same with this one, we can remove it, and this one. So this would be a little more space efficient, but since we are still saving the elements, it would still be a big O of n complexity. So a different modification. So what if instead of finding the first non-repeated element, we are looking for the first repeated? How could we improve our previous solution, or actually, how could we change it? So we no longer care about the count. Going back here. Now we're trying to find the first non-repeated one. or the first repeated element, which would be negative 234, right? So we don't care about the count anymore. And this is because if we look for negative 234 in our map and we find it, that means that we've seen it before. So as long as it's there, when we search for it, we can return it right away because we know that it's repeated and it's the first repeated one we see. Since we don't care about the count anymore, we can kind of like ignore the value associated with each key. We only care about the keys now. So do you guys think there's a better container that we could use instead of an unordered map? So this leads us to talking about sets. An unordered set it has the same functionality as a map, except that it doesn't go to a value. So instead of going from a key to a value, you're only keeping track of keys. So it's kind of like you had like a big set with like key 1, key 2, and you just know if you've seen them before. So in our problem from before, every time we saw an element, we would put it into our set. So we saw negative 234, we saw 1, we saw 2, and then we saw our next entry was negative 234 again. So when we searched for it in the container, we would see that it was already here. And then we would know that it's repeated. So we could right away say that it was repeated. So again, here's the implementation. So when we find if it's equal to the end, if it's an end iterator, that means that it's not in our set. So we would insert it. But if it was not the end iterator, that means that it's already in our map. So that's like a statement here. So we would know that this is the repeated number. So once more, sets and maps are very similar. Again, it also has average big O of 1, worst case big O of n complexities for finding and inserting. So same as a map, we just don't have a value associated with our keys. Okay, so far we've been looking at unordered maps and sets, but ordered ones also exist. The difference between them, as you can imagine, is that the ordered versions maintain like some order, some sort of like sorted order. So for example, it might sort based on like ascending like value or descending or anything like this. The complexities do change if we want to maintain the sorted order, because now instead of like just finding the next available spot and like inserting something into it, we need to keep this sorting like invariant, right? So now our complexities would be big O of log n for insertion and for finding. But it is useful sometimes, especially if you want to do something only if like the value or if the key is like more than 5 or something like this. So this is how you would declare the ordered version. You just avoid the unordered one, the unordered part. So this is ordered. Oh, sorry. This is unordered. This is not. Same with maps. All right. So do you guys have any questions about maps and sets before we move on? Cool. In that case, we can go into Enum classes, which are also useful for project 3 and just good practice and something good to keep in mind. So if you remember for project 1, we wanted to keep track of the mode of your mode, right? You could have like stack mode or queue mode. And we told you not to use strings for this, since that would be like a very expensive like comparing like every single character in your string. So instead, you guys may have used a character or an int. But instead of doing this, you can use an enum class for an enumerated type, which is the same kind of logic. Like you have a type whose values are restricted to some set of values. So for example, here mode can only be stack or queue. So you could create an enum class in this way. So you would say enum class mode, and it can be either a stack or a queue. So this is a lot more readable because now instead of having to look up S or Q to determine your mode, you can simply look stack and queue. And it's just as efficient because this is implemented using integers. So to us, they look like stack and queue, but to your computer, they're just like a 0 and a 1, for example. So we know what they mean, but it's still a lot more efficient. So here's another example. Say that you know that you're going to be using colors a lot for a program, and your colors can only be red, green, and blue. So you can create an enum class color with these 3 colors. And then you can choose your favorite color and you declare it like this. So your type is color and you choose color red. So now if your favorite color is red, you do something. If it's green, you do something else. And if it's blue, you do something else. So again, we can do this because our values are restricted. There are only 3 possible colors that we're looking at. And using an enum class makes it like really easy to tell what's going on, because we can see that we're looking at what happens if your favorite color is red, or if it's green, or if it's blue. So if instead we wanted to like keep just an integer and say 0, 1, and 2, someone who's not familiar with your program and you're saying if your favorite color is 0, you're going to be like, wait, what is 0? Is 0 purple? If you're looking at it and you didn't write it, you wouldn't know what's going on. So enum class avoids this. Enum class like tells you specifically what color you're looking at. Again, so enum values are represented by an integer type. That's why they are efficient, because even though you have like a value that you're looking at, it's actually represented with a number. So if you don't say explicitly what numbers you want, what integers you want for each of your types, they will by default be 0, 1, 2, 3, and so on. But you can change them to be something else. So for example, if you want C to be 10, you can tell it to be 10. Then D will be by default 1 more than that, so 11. So you can change the values in case that like you want to compare them and get something specific out of them. So which means that you can use these operators in your enum classes. So you can ask something like, is color red equal to color blue? And of course, this would return false because they are not equal. They have different like integer values. If you want a different type than integer to represent your enum class, you can. So for example, if it was too big or too small, you can use something else, and you can use a character. You can change this to be anything you want, but the default is numbers, and the values go in ascending order. Now for emplacement. This is also useful for the project. So let's say that we have a struct called foo that has an integer a and a character b. And we want to create a vector of these foo structs. So if you wanted to add a new entry into your vector, you might want to try to create a copy of foo and initialize it with 70ng, for example. And now this is what you would usually do, but this is not great because this is calling foo's default constructor. So it's kind of like creating foo here in this like stack frame. But then after that, it's also moving it into your vector. So you only want it inside of your vector. But if you do this, you're creating a copy outside of your vector that doesn't really have a purpose. So it's just, you're doing unnecessary work that you could avoid doing. So the solution to this is to use Emplacement. So Emplacement and pushback are very similar. But as you can see, the parameters that it takes are the same as the ones that you use for your constructor foo object. Instead of pushback takes in a foo object. So if you use pushback, you call foo's constructor and you create an object, and then you move foo into the vector. But if you use emplaceback creates foo in place. So it goes directly into your vector, looks for the next spot, and it creates foo right here. So it saves the extra move and the extra copy that you would have had with pushback. So it's just more efficient to do it this way. The parameters to emplace have to match the parameters to the constructor in your container's data type. So here you can see that you construct a foo object by using an integer a and a character b. So if we emplace back on a vector of fighters, then we want to provide a value for this integer a and this character b, which is kind of similar to what you would do using pushback, but you would give those two values to the foo constructor instead of to emplaceback. Okay, now using declarations. So at the very beginning, we had an example of this where we were using a name and something else, but we were using strings basically. And we were telling our compiler that every time we used name, we were actually referring to a string. So this is where the using declarations are useful. So say, for example, that you want to have a map that goes from some key type, so say that it's an integer, to a vector. And this vector contains other types. So right away, you can see that this looks like really clunky, like it's a really long declaration for an unordered map. And then if you want to create an entry inside of your map, you also need to do that all over again. You need to say std vector of other type. And this is kind of clunky and kind of harder to read if you're looking at it, right? So we want to find a way to avoid doing this. So instead of having to type out every single thing in here, we want to use an alias or something that we can use in place of this. And this is where using comes in handy. So if we say using row is equal to std vector other type, we are telling our compiler that every time we use row, we actually mean a vector of other type. So these are now equivalent. Row is the same as vector other type. But row is a lot easier to write, and it's a lot easier to tell what a row is, right? If I just give you a vector of other type, you're going to be like, well, that could be anything, right? Just a vector. But if you read that it's a row, then that just makes a lot more sense, and it's just more easy to understand what the program is doing. And it saves you a lot of time typing this whole thing out. And you would use row just as you would use the vector of other type. So for example, here, if you wanted to create a vector, you would give it the size and the default value. Well, you would do the exact same thing if you were using a row, because a row is a vector. So you give it its size and its default value. So once more, row and this vector are equivalent. Okay, and that's the end of the content for this lab. Now I'm just going to go over the handwritten problem. But before we do that, do you guys have any questions about anything that we saw in the lab? Okay. If not, I'm just going to quickly go over the handwritten problem and then stop the recording, and you guys can stay here and work on the handwritten problem. So given an array of distinct integers, we want to find if there are two pairs, AB and CD, such that their sums are equal. And all of these A, B, Cs, and Ds are distinct elements. So if there are multiple elements, the function should print all the pairs that work. Okay, so here's for example, if we get this array of distinct integers, we want to return all the pairs that have the same sum. So for example, 3 and 2 and 4 and 1 both sum to 5. So we would want to return those. So right, so 3 and 2 would be one of your pairs. Right, so 3 plus 2 is equal to 5. And then we can do the same for C and D, which would be 4 and 1. And you want to do this for all of the pairs. And if there are no possible pairs, then you just output nothing. And what we mean by all of them are distinct elements is that you can't do something like, for example, say that 3 and 4 and 4 and 3 have the same sum, because they do have the same sum, but you can't reuse an element. And a similar example would be if you also had like a 0 in your input. So you can do that. You couldn't say that 8 and 0 and 4 and 4 have the same sum, because 4 and 4 is again repeating one of the elements, and we want all the elements to be distinct. Okay, so your expected runtime will be big O of n squared, and here's the function declaration. So just make sure you submit this on Gradescope by Friday, and I'm going to stop the recording now, but you guys feel free to stay back and work on this and ask me for help or any other questions you may have. But thanks for watching this if you're watching the recording.